this is bigger than or equal to, so this will become 2 minus 2 times of rho xy. Okay, so 2 minus 2 times of rho xy. So this divided by sigma x sigma y is rho xy. So on the other side you have greater than or equal to 0. So this means that 2 minus 2 sigma xy is greater than or equal to 0. So if you divide by 2, this shows that sigma xy is less than or equal to 1. So you really got to this actually. Okay? So xy is always less than or equal to 1. And if you want to compute, for example, the other side, just compute this for minus actually. Okay? And you will see that this is going to reveal that sigma xy is bigger than or equal to negative 1. So the correlation lives between what do you call the quantities negative 1 and positive 1. Okay. So let's move on. Let's move on to our next important topic, which is, so calculating the covariances is not difficult. You just the correlation is not difficult. You just need covariances of the random variables and the variances of it. So the next thing that we would like to move is the idea of the conditional expectation, and doing some examples on it and proving some properties of the conditional expectation. Okay, so I'm leaving some examples and exercises for you to work out for yourself. So it is important to make sense of those computations and ideas and interpretations actually. So let's define the conditional expectation. Conditional expectation is one of the topic of the prime importance in the theory of random variables, stochastic processes, stochastic calculus, even in the theory of modern finance actually, okay? Theory of asset pricing. Because all of the asset prices, so if you're considering to buy an option, you're considering to buy making some investment, okay, into some kind of securities actually, and you want to find the prices of those, the fair prices of those securities, okay. Then what you can prove, okay, so maybe when we're going to do the course on the finance, we're going to prove what you call the Feynman-Koch formula and show the fundamental theorem of asset pricing that a fair price of a security in a complete market, okay, in a complete financial market is really the conditional expectation actually, okay. So it's a conditional expectation of the payoff, okay. It's the conditional expectation of discounted payoff actually. So conditional expectation is something that we're going to encounter more. Okay? So we're going to talk in more detail about the more sophisticated versions of the conditional expectation in our course on stochastic calculus actually. So the conditional expectation is also something important. So let's recall before giving the definition of the conditional expectation that what was the conditional PDF actually. So the probability of the event that, so this kind of represent the PDF, the conditional PDF. We defined it that in the manner that the conditional PDF of x given y means that the probability that x is x and y is y actually. Okay, and then we can write this as, okay, the probability of x equal to x and y equal to y divided by the probability of y equal to y. Now this above quantity is really the joint PDF of x and y, and the below quantity is the CDF, the marginal PDF of the random variable y actually. So we know this is stuff. So we're going to use this in a minute actually. Now, what would be the conditional expectation? So I want to define the expectation of x given y equal to y. So expectation of the random variable x given y equal to y. So if I give you an opportunity to define this, the expectation, this kind of expectation, so think for a moment, pause the video and think for a moment that what should be the definition. Now, how to compute the expectation of, say, random variable x? So we say that, okay, take your values of x, okay? So take that what values x takes and multiply them with the corresponding probability. So the conditional expectation, say for example in discrete case, is going to be precisely same, that x takes some value x and multiply this with the corresponding probability that x is x actually, but don't forget this given information, given what we call y, okay, and sum up on all such x actually. So if x takes, some values, take those values and multiply them with the conditional PDF actually. So this would be the definition of the conditional expectation for the discrete random variable. Okay. So this discrete random variable, in other words, if you write this as that this is x times the conditional probabilities of x given y. Okay. So this is what is the definition for it actually in discrete case. And obviously in integral case, this is going to be the integral, so expectation of, say, x given y equal to y is going to be an integral from minus infinity to infinity, x times the conditional PDF of x given y and integrated with respect to dx. So this is what is going to be the definition of the conditional expectation in case your random variables are continuous. Okay. Let's do some examples of computing the conditional expectations. Okay, one in the case of the discrete and one, say, in case of the continuous time. I'll leave some exercises for you to do the computations. So here is the example 5a from the book. So it says that imagine x and y are two binomial random variables, okay, with parameters n and p. So x is a binomial random variable and y is binomial random variable with n and p. In other words, x and y are identically distributed, okay, and assume that x and y are also independent actually, okay. So they are independent random variables. So x and y are binomially distributed and independent. Now compute the conditional expectation of x, okay, the conditional expectation of x given x plus y is equal to mn, okay, given x plus y equal to m. So this is what that we have to kind of compute actually. What could be the scenario that it can model? For example, you can say that, okay, x is representing say a number of say heads, okay, in n throws, okay, where the appearance of the probability of head is b, okay, like 1/2 for example, and y represents number of tells actually. So you want to know what would be the expected number of heads given that the total number of tells and heads is equal to what do you call m actually, okay, it's equal to m. So let's compute this. So in order to compute this expectation, we need to first find, you know, the joint PDF actually. So let's calculate this first. So let's compute. So I want to compute probability that x is k given that x plus y is m, okay, where k is some number that is less than or equal to minimum, okay, that is less than or equal to the minimum of n and m actually. Okay, so it's less than or equal to minimum of n and m. So let's calculate this probability. So this would be same as having probability of say x equal to k and x plus y equal to m and everything divided by x plus y equal to m. Okay. Now why we assumed k is the minimum of n and m, because we want to make sense of this number actually, this probability. So if the probability, so this is x is k, okay, and y, x plus y is m, so y would be m minus k actually, okay, and everything divided by what do you call the probability of x plus y equal to m. Now x and y are two independent random variables, so I can say that this is same as probability of x equal to k times probability of y equal to m minus k. Okay, times the probability of x plus y equal to m. Now you can see another reason that why you took k to be n, a minimum of n and m, so that x and y can have the value in the arranged range actually. So that in other words, the value that x takes should not go beyond n, and y, the value of y should also not go beyond n actually. Okay, so if you have this assumption, this must be true, because k is a number that is less than or equal to m, and k is also a number, and m minus k is obviously going to be also less than or equal to m actually. Okay, so you have this. Now I know about x that it's binomially distributed, I know about y that it's binomially distributed, and we also know about what do you call sum of the random variables, that if you have two binomially distributed random variables and you summing them up, their sum is also going to be binomially distributed. Okay, so recall the fact. So I hope that you did this that exercise that I said that you should do it in your last class actually, that if x is a binomially distributed random variable with say np, and y is say binomially distributed random variable with say mp prime, then x plus y is a binomially distributed random variable with n plus m p prime. Okay, and p plus p prime. P plus p prime. So based on this observation, what would be the distribution of x plus y? So if x is binomially distributed with np and y is also binomially distributed with np, so that x plus y is going to be the binomially distributed with a random variable. I think this, so if it is also p, then this would stay p. So if x is binomially distributed with parameters n and p, and y is binomially distributed with m and p, then x plus y is binomially distributed with n plus m and p. In other words, that the probability of each Bernoulli trial is equal for all, what do you call, trials actually. So x plus y is going to be the binomially distributed with 2n and p. And once we know this, then I can directly write this expression, that the first expression is going to be n choose k, okay, p power k and 1 minus p power n minus k. The second is going to be n choose m minus k, p power m minus k, and 1 minus p power n minus m plus k, and everything divided by what do you call, x plus y equal to n. So the x plus y has a distribution 2n, so it's going to be 2n. Okay, so 2n choose m times p power m, and 1 minus p power 2n minus m. Okay, so this is what it is going to be. Now, if you simplify it a bit, so the p power k will be cancelled with p power minus k, and the p power n minus k would be cancelled with, what do you call, so in other words, if you sum them up, so this is going to be 1 minus p power n minus m actually, because k and k will cancel out, and here also the k and k will cancel out actually. Okay, so you're going to get what? So you're going to get, okay, so if k and k are cancelled out, so you're going to remain with p power m, but the p power m is also here. And if you combine these two terms, the k and k will cancel out, and you're going to get n minus m, and you also have n plus m minus m, so 2n minus m. So these probabilities basically cancel out with each other actually. And what remain is really this number, which goes like n choose k times n choose m minus k, and everything divided by 2n choose m. Okay, so this is what is going to remain. So once you have this, we have this PDF actually. And once you have this PDF, now you can apply the definition actually. So what would be the expectation of x? The expectation of x given m plus 2 is going to be a sum. What would be the expectation of x given, what do you call, x plus y equal to m. Okay, this is what you're going to have. So this is going to be equal to, what do you call, the sum that goes from, say, x equal to 0, okay, to n, and x multiplied by probability of x equal to x, or maybe if I put a k here, so k equal to 0 to n, probability of x equal to k given, what do you call, x plus y equal to m. Okay, so once you have this, just substitute this formula, k equal to 0 to n, and k times of, what do you call, n choose k, n choose m minus k and divided by 2n choose m actually. Okay, and I'm leaving this sum for you to figure it out, that how this sum would be equal to this would be equal to what you call a number m upon 2. So it's going to be m upon 2. Okay, so I mean, if you have done say example say 2g, okay, from this chapter, then you already have done this calculation actually. Okay, so otherwise, I mean, first try to do it for yourself. If not, go to the example 2g in book and try to make sense of this calculation actually. Yeah, you know, just think carefully about it. Okay, try to create a combinatorial argument or a story proof that this sum would be equal to m upon 2 actually. Okay, so I'm leaving this for you to figure it out. By the way, one thing which is going to be interesting, that this number is independent of k, so you can pull this out and then think about these three numbers. Try to create a story through which you can reduce this actually. See the example 2g. So that's how you compute, for example, the expectation of a discrete continuous random variable actually. Conditional expectation of x given a discrete random variable given another discrete random variable. Let's do an example from continuous time. So imagine you have been given say f of xy, joint density is given f of xy equal to e to the minus x over y and e to the what do we call minus y, okay, where x and y both are between 0 to infinity. So they are between 0 to infinity. There is no relationship between both, so the compute expectation of x given y equal to y. Okay, so this is example 5b. Okay, so this is the expectation that you need to kind of compute actually. So in order to compute this expectation, by the way, here we don't know, unlike previous example, that x and y are independent or not actually. So x and y are not necessarily independent actually. So first of all, what would be the PDF? It's better to settle out first PDF. X given y. So it's going to be, we know that this is going to be f of xy divided by, joint PDF of f of xy divided by the marginal PDF of y. How can I compute the marginal PDF? Joint PDF, I know that it's going to be e to the x over y times e to the minus y. The marginal PDF is going to be, you can compute it as integrating from say 0 to infinity, because that's what is the domain. The joint PDF with respect to x. So if you integrate the joint PDF with respect to x, you're going to get the marginal PDF actually. But in this domain, what is the value of joint PDF? So it's e to the minus x over times e to the minus y and dx. This is what you're going to get. So if you simplify this expression, there is also y and divide actually. So if this is the case, you're going to have divided by y, and you're going to also have something that is divided by y actually. Now if you compute this, so this integral is with respect to x, so you can just take this e to the minus y by y outside, and the integral of x minus x divided by y, in other words you can treat it like a constant actually, is going to be e to the minus x over y divided by minus 1 over y actually. Okay. So in other words you can compute this integral. Maybe here's this little bit of computation, not difficult. do. By the way, this is also obvious. This is also obvious that e to the y and e to the y are independent of this integral, so you can pull it out, and if you wish, you can also cancel them out actually. Okay? And same thing you can do with the y actually. So the y is also independent of this integral, because this integral is with respect to x, so you can also cancel this y as well. So what is going to remain is going to be e to the minus x over y divided by the integral of e to the minus x over y, so it's going to be e to the minus x over y divided by minus 1 over y. Okay, so this is what that you're going to get, and then obviously you need to put the limits as well. Okay, you need to put the limits as well. But okay, even if you put the limits, what you're going to get actually. So this minus y, e to the minus x over y will become minus y divided by e to the minus infinity minus e to the 0. Okay. So this will become 0, this will become minus 1, so what you're going to get is y e to the minus x over y. So this is really the joint PDF of the result. And then what you have to do, you compute the conditional expectation of x given y equal to 1. So this will be the integral from 0 to infinity x times the joint conditional PDF, which is y e to the minus x upon y with respect to dx actually. This is what that you're going to get. And if you pull out this y, okay, by the way, this y would be in division. Okay, so you have to be careful. This y is going to be in denominator. So if I can pull out this y and compute the integral, it turns out that all this integral would be equal to y. Okay? So the average value, if the CDF is like this, the average value x given y of x is going to be the value that y takes actually, in other words y. Okay. So this is what is really one of the simple example of computing the conditional expectation actually, in discrete case and continuous time case actually. Now obviously, as you have a formula for computing the conditional expectation of say discrete random variable x and continuous random variable x, so you can also have a formula for conditional expectation of discrete random variable of the function of x and function of y. In other words, if you want to compute say the conditional expectation of say g of x given y equal to y, then this would be equal to the sum over x, the values that the random variable x takes, times g of x multiplied by the conditional PDF actually. Okay, so g of x multiplied by the PDF. In other words, that compute the g at the each value that x takes and then multiply it with the conditional PDF. And the case of continuous time random variable, okay, the strategy is going to be the same, that you integrate say over say minus infinity to infinity g of x multiplied by the conditional PDF of x given by dx. So this is what is going to be the conditional PDF. Okay.